All right, everyone. Welcome, everyone. I hope you're having a great NZGDC. What are we, like 20 years now? My name's Keegan Gibson, and I'm a senior programmer at CerebralFix. If you see our shirts around, do come say hi. There's like 30 of us here. And they're really nice people. Also, big thanks to Epic Games for inviting me here to speak. There's a few of them around as well. Say hi. They're also lovely. Today, I'm going to tell you a little bit about Nanite, or as the cool people call it, virtualized micropolygon geometry. It doesn't quite sound as cool, it sounds super technical, but Nanite sounds far less scary and way more magical. But it isn't, it's clever code, but it's not magic. So hopefully what I'm going to do is demystify some of the common things I hear people saying about Nanite and what I see on YouTube, which makes me cry, by exploring how it works, delving into the situations where it doesn't, and the situations where it likes it the least, so that you can see what it's doing and why. And in turn, how we can maybe author our assets such that they make better use of Nanite. And at the end, if we have time, I'll dig a little bit deeper into how to performance profile Nanite, should you need to. Can I get a quick hands up? Who are the artists in the room? Do we have any artists? Woo! And the programmers? Woo! And my favorite people, the others. Welcome. So for the record, I'm a programmer, not an artist, so take everything you see visually here with that lens, because I made it. Well, or I assembled it. So what is Nanite? Nanite, virtualized micropolygon geometry. We kind of throw this word virtual around in the engine a lot now. We have a lot of virtual systems in the engine, virtual textures, virtual shadow maps, virtual file systems. But all it really means is that we're using a sparse set, a subset of our data, and just loading that, just sending that to the GPU, and just rasterizing that data. So that means we're only storing that in memory, only the bits we really need. So what's virtual about Nanite? Well, Nanite takes a subset of our geometry, our vertices, our triangles, and sends it to the GPU, rather than the entire mesh. Because even if we had 3 million polygons, it's highly unlikely that we're rendering all of those polygons at once. They'll either be behind the mesh or off screen or behind something else. And so why do we need to do this? Why do we need this virtualization tech? Have the programmers just gone wild writing cool code? And we do. So we used to just throw a couple of things on the GPU, a static mesh here, a texture there, a little bit of other data. But now we're adding more and more data, larger meshes, larger textures, distance field, lumen data, virtual shadows, particle systems. And our available GPU memory really hasn't been increasing at the same rate as we're consuming it. So this is where our virtualization comes in. We need to get more efficient with our data, more efficient with the time, both in CPU and ourselves. Starting with the largest set of data, Unreal introduced virtualization systems. So first we got virtualized textures and then shadows and geometry. So with that, you might start to think that Nanite's only for the big stuff. It's only for my high resolution textures. It's only for millions of polygons. No. If it can be virtualized, it should. Does it help with our high resolution data? Yes. But it's not just for the big stuff. And it's important to understand how these virtualized features are working so that we can better take advantage of them and not fall into any traps. So, through the things that Nanite likes the least, we're going to illuminate, and that's an engine pun, you can have that one for free, what Nanite is doing. So let's take a look at some of the buffers that help us visualize what's happening behind the scenes. So first I'm going to bring up our Viz overdraw, which is my one I love to hate. So you've heard of the brightness of 1,000 suns. I give you the brightness of 1,000 trees. This visualization buffer is showing triangles that had to be rendered on top of each other in order to compose the scene. So, one mesh on top of each other. This can be why some of our foliage scenes tend to perform worse than, say, like rock-based scenes. But I also really want to make a note here that just because you have overdraw doesn't mean you have a performance problem. Typically, I see this as like the go-to thing when diagnosing problems, and it's really the wrong methodology. I'll get into that a little bit later, but yeah, if you have overdraw, doesn't mean you have a performance problem. So let's evaluate here what might be so expensive about the scene and start dispelling some myths about Nanite. So what does work well in Nanite? Well, contiguous geometry. This is geometry that's connected together. The vertices are all connected together. The more connected, the better. So what Nanite is trying to do is draw the best version of that asset from that particular view. So when an asset is imported, it breaks down the mesh into a bunch of clusters of geometry of vertices and splits the geometry up, usually to around like 128 triangles, give or take, and then further simplifies down the clusters of clusters. So it's kind of like the log system of old, but we're only doing it for like parts of the mesh. So let's have a look at our clusters. So we can look at another buffer visualization for clusters. And this is a great visualization of how Nanite has broken down these meshes. So effectively, it's only drawing the clusters that are on screen. And if we zoom in and out, we can actually see the clusters changing over time as we go in and out of our clusters. And what it's doing is now it's picking the best set of clusters that will best represent this asset. So the further I get away, it's going to drop the number of triangles back. It's going to go back to a LOD. And this is where Nanite gives us near pixel perfect LODs, which is really exciting. So yeah, as we move around, Nanite is streaming in and out of this data, depending on what it needs to best represent it. If that geometry is not connected, like at the edge of a mesh, or say a leaf on the edge, which tends to just be, leaf cards, then it's nowhere for Nanite to crunch that data to. It's got nowhere to go. There's nowhere to decimate that and maintain the volume and maintain the shape of that asset. Slight tangent here, and I'm going to go off script and I'll regret it later. When Nanite is simplifying down this geometry, what it does, it's actually just lerping between the vertice data in between. So if it needs to combine two or split two, it's lerping between them, which does mean it's lerping our UVs as well, which can be quite painful if you don't want that to happen, like if you're using vertex animated textures or you need explicit texture UVs. So as of 5.4, there's this new checkbox called lerp UVs, and if you just untick that, you will now get explicit UV vertices, which is really cool. But for the most part, we want it to kind of, figure it out for us. It's really kind of concerning me every time because my go to full screen button is also on the airplane mode button. And every time I'm like, I'm about to lose everything. Cool, what else does Nanite like? It likes blocking assets. It likes assets that occlude the world. And this is the efficiency of Nanite. So we'll go back to our overdraw buffer again. Where are we? Overdraw. And you can see as I move around, that rock mesh that is behind, none of that's getting rendered. But I can still see the top of it. So the top part of that mesh, which is in there, is getting rendered. So it's slicing the vertices, so I can only render the parts of the meshes that I need to see, the parts I care about. So if I can't see a cluster, it's not drawn. Now these clusters are bounds culled, so if you have large clusters, they're going to have large bounds. So that has another effect on how we author our meshes. If we have long, thin triangles going across meshes, then those cluster bounds are going to be big. So if even a little part of it's seen, we're going to render everything behind it. So that's where you might end up with a little bit of overdraw. Cool. What's next that Nanite likes? Non-layered geometry. Nanite doesn't love layered or intersecting geometry. As we said, clusters are culled by bounds. So if you have tightly packed geometry, we can't cull them. So as we're building out our world, we might want to be just a little bit more careful with our kit bashing ways. Like I said, these are not really performance problems until they are. I'm over this buffer visualization already, but here we go, overdraw again. We can see a few hotspots here, and this is a section where Nanite can't determine which cluster should be shown. And so it renders all of them and lets the GPU take care of it. So yeah, effectively what's happening, I'm seeing parts of these clusters, and I'm having to render it. Now I've cheesed this example a little bit, and I have just nodes and nodes of rocks stacked underneath each other to demonstrate the problem. But you can see how this might become a problem. So as we're thinking about, instead of thinking, can I see a whole mesh, we're now saying, can I see clusters or micropolygons of geometry? And it's the same for virtual textures, right? If I don't need the whole texture, I won't send the whole texture. I'll just see the parts that I can see and just send them to the GPU. So virtualized textures, virtualized geometry work really, really well together. So if we start putting that all together, back to our forest scene here, what have we got? Layered geometry, geometry that includes the world, and contiguous geometry. And if we take a look at our forest, we have individual elements that aren't connected, your branches, your leaves. They're not actually vertically connected to the trees. Leaves have their own cards, they're disconnected, the branch is disconnected from the trunk. So if you imagine as we're trying to decimate that geometry down, there's nowhere for Nanite to go to maintain that volume. Occlusion. Leaves and twigs suck at occluding other leaves and twigs. They're filled of holes, they're moving in the wind, which I'll get to a bit later with world position offset and why that might be a problem. So it gets really hard for Nanite to determine which triangles and clusters are important. And then layers. Well, our forest is nothing but layers of geometry. Now these performance issues can be quite small until put into the wrong situation. It's just something we need to be aware of. But it does demonstrate to you what Nanite is doing under the hood. And it's clever. And if we take a look at our clusters, again on the trees, that one, you can see as I move around, we're not really getting a lot of changing on the clusters because there's nowhere for this data to go. Right, the next thing I want to talk about is size on disk, which, it's kind of an interesting one, but it should be talked about. Both of these assets, the rock here and the tree, are the same size on disk. The same size in Nanite, roughly 25 megs, but the rock has 4 times more vertices than the tree does. And that's simply because we can do stuff when we have connected geometry. So how can we work with this? Well, when we build a tree, and who here's built a tree? Oh yeah, there we go. When we build a tree, we tend to build it out of its components. We have a trunk, we have branches, we have sprigs, and we have leaves. And we copy and paste them randomishly around the tree, and bam, tree. At least that's how I understand it. And really, we have a bunch of unnecessary duplications that look like unique geometry to Nanite, because it can't tell that you've just copy and pasted it and baked it all around. So instead of baking that mesh, we could composite one. By creating a PCG or procedural content generation, we can procedurally generate a tree and effectively instance that data rather than it being unique meshes. So I have here a couple of procedurally generated trees. I know you couldn't tell. And as I move this around, I can get really different results, which is kind of interesting. But what does this mean? Well, because Nanite's now just got a fixed set of mesh that it can work with, it can do something. It can actually do a little bit of clusterization work on it. So if we look at our viz clusters now, this is another forest made up of that tree, and we look at our clusters, and we start moving around, we can actually see we're getting some cluster work happening now. We can actually, and these are all instanced static meshes around the trees. So what it is, I instanced that mesh, I baked it into a level, and then I procedure generated that level around. So yeah, what's Nanite doing? Importing our mesh, splitting it up into clusters, rendering the visible clusters. Now, and remember, if I'm saying if you have overdraw, doesn't mean you have a performance problem. This is just a tool to describe how Nanite works, and we still have overdraw now. I can show you. There's still some there. Doesn't mean we have performance problems. But what happens if we do have nanite performance problems? What can we go about doing with it? So these are some settings in Unreal that you can just do out of the box and get a bunch of free wins on performance. You can set your world position offset a draw distance in world partition. This means that at a certain distance, we're no longer going to be evaluating the vertex things and putting the wind on our foliage, which is always nice. Nanite doesn't love it. We can turn, if we're doing a full Nanite and Lumen game, make sure Nanite's on, turn virtual shadow maps on. I highly recommend, if you're using Nanite, to also be using virtual shadow maps. These systems were made to work together, and they work really, really well together. Make sure you've got virtual textures on, because now we're using more virtualized stuff. There is another option to allow static lighting. Turn that off. We're using Lumen. We don't need it. We're fully dynamic, so we can turn that off entirely. We've got our Lumen on. There's a couple of other really interesting settings as well. If I take a look at our project settings, and I say turn reversed, give me index buffers. Cool, so there's two options here. They're on by default. There's support reversed index buffers, and all that is it's storing a copy of your index buffer, but backwards. And this means you can negatively scale assets for a minor speed improvement. Please don't negatively scale your assets in the world. You'll make your programmers cry. So turn this off, and you save an entire duplication of your index buffer, which can be really important if you've got large nanite meshes with millions of polygons. You've got large index buffers. The other one we can turn off is our depth-only index buffers. And these are storing another copy of our index buffer, but Nanite's doing its own depth information on it. We don't need that data. So you can turn this off and save a bunch of memory, which just has a lot of flow-on impacts to performance. And these are available for you to just go right now and go start turning things off. You can still negatively scale assets. It won't stop you, but please don't. Cool, so after we've done all our nice tick box settings in the editor, because there's always nice tick box settings in the editor, how do we go about debugging Nanite? Well, first of all, I would say don't optimize unless you have a problem. Don't over-optimize ahead of time. If you don't need this, don't do it, and validate your assumptions. Standard debugging practices, make sure you've got good data so you can say that if you change something, it actually worked. So my first go-to is the classic stat FPS. Because, what is actually my FPS? Stat FPS. The other one I like to turn on is stat unit. Now, you don't have to memorize these. They're actually in the hamburger menu up here too. There's the stat thing and the engine. You can turn on your FPS and unit up here as well. So what are we looking at here? So here we're looking at our thread times, basically. Where is all our time going? So the frame time, I don't know how hugely readable this is, but there's a frame time there. Your frame time is your combination of your draw and game threads. These two threads run in parallel, but they do have to sync up to complete a frame. So your the game time there is on your CPU side, and it's usually your game logic. So it's usually inside your tick functions, and it's running all your game simulation logic. The draw thread is the CPU side of the rendering thread. So it's issuing all the draw commands. Now, if your game time is close to your total time, then you might want to look at your game thread performance. If your draw time is close to your total time, you might want to look at your rendering thread performance. So these are good places to start. But say, you've determined that Nanite does have some problems, or you believe it has some problems, where are we going to start looking? And it's outside the budget that you want to allocate to Nanite. So another one we can turn on here is r.nanite.show mesh draw events 1. And that's going to, when I do a performance profile on the GPU, it's going to give me a little bit more information about Nanite that I can actually go for. So I'm going to bring up the GPU visualizer, which is a Control-Shift-, it's going to open on the other screen. Yeah. And so now I can start looking through and evaluating what in Nanite is taking up all my time. So if I scroll down here, and actually I'll do it on a more interesting scene. There we go. And it's still on the other screen. All right, so if I have a look down here, and hopefully, I don't know how readable this is, down here I'm looking at my scene, and Nanite viz buffer, draw geometry, then the main pass, and I'm looking at my hardware and software rasterizer. So there's two things in here. There's the fix function, which is your opaque, non-deforming meshes, and then there's all the other meshes, all the other materials below it that need to what we call programmable pixels or programmable rasterization. These are things where it has to do some sort of calculation to render that pixel first. So the first thing we want to evaluate is, where is our cost? Is it in our fixed function rasterization, or is it in our programmable rasterization, or the accumulation of our programmable? So if we think that, or if we see here that our programmable is high, okay, where? So let's start looking a little bit further. Back in our Nanite visualization, we can look at evaluate WPO, or evaluate everything that's using world position offset. So all the things here in green are using world position offset and having their vertex shader evaluated 3 times per pixel, which already sounds expensive, doesn't it? And that's because these trees have wind. However, if this was mostly red, we might think, well, maybe it's somewhere else in our programmable pipeline, but this might be, somewhere to start. So if this was mostly red, I would switch to a new view that's in 5.4 called Pixel Programmable. Now, if this is mostly red and my programmable cost is high, then I might assume I either have a lot of masked materials, materials with pixel depth offset, dynamic displacement, etc. And pixel programmable shaders always have to be evaluated. So, maybe I can start looking and go, is it in some of those materials? If it's neither of those, and our fixed function performance is high, our opaque, non-deforming geometry, then that's where I might start looking at applying some of the techniques we talked about earlier. Our overdraw, our occluding, contiguous mesh intersections, that kind of stuff. And we can create meshes that better serve what we're doing. So back in overdraw, if I look here again, if you look behind here, you can kind of see that the door is still getting rendered, even though it's fully behind this thing. And that's because if we take a look at our wireframe mode here, the walls have big long triangles, which is perfectly appropriate for this type of asset, and thanks Cindy Studio of Auckland, because that's where I bought the asset pack from. So yeah, big long triangles means that cluster is going to always be rendered because it's going to have large bounds. So while it's being really good at occluding the world, it really sucks at being occluded. Those are the kind of things we can look at. One of the other things I want to look at is maybe we're just rendering a lot of things. So how do we know if we're just, what's our effective draw calls as it used to be? So we're going to turn on another I'm going to turn off the other ones first. Stat FPS, stat unit. And I'm going to turn on Nanite stats. And that's probably even harder to read, but if you look down the bottom here, there's shading bins. And if you subtract the empty from the total, that's kind of like sort of your effective number of draw calls. It's gotten a little bit more confusing now with variable rate shaded Nanite, but that's like how many meshes we're currently, or how many of the clusters we're currently drawing. So if we have a lot of those, then maybe we want to be thinking there as well. The other possibility is your materials are just expensive. So maybe you need to go look at what is actually happening in your standard materials, and because Nanite still has to rasterize those pixels from somewhere. So you might want to dive into material performance at that point, and material performance debugging. So in summary, Nanite isn't magic. It's very cool, but not magic. It's not about rendering millions of meshes or about rendering meshes with millions of polygons. It's about being efficient. And it's really going to come down to what makes sense for your game. And I hope this has been a small insight into some debugging tips, and hopefully demystifying a little bit of what Nanite is doing behind the scenes for you. I've rattled through that at a lightning pace. So does anyone have any questions? Or does anyone want me to go back and explain something a little bit more? So I talked fast. Yeah.
Great talk, thanks so much.
Yeah.
Yes, the first question I had was more about pipeline changes that you've been in the studio. Obviously now moving towards utilizing Nanite production. One thing you were mentioning was about how, I guess, you don't want to have triangles in your meshes. Sorry. You're okay.
I will repeat the question.
Yeah. You don't want to have long triangles on, things like really long bits of wood or something like this. That's probably a little different to what your previous art production pipeline was like. We were involved in those changes. Recommendations of how you want to do asset production going forward?
So the question is, how do we validate our asset pipeline and perhaps provide feedback a little bit earlier into the pipeline around changing the way we model? If you caught Jack Condon's talk a little bit earlier, you could probably look at an interchange pipeline, which might be kind of interesting for it. For us, it was really about just education around our art team. And helping, I gave this talk to them in the studio. It's really, and giving them access to the buffers as well, so they could see what was going on. Exposing them to that, I think, was really where it was. But if you have a way to sort of start looking at this in the pipeline creation, I'd love to hear about it, because that would be cool. Yep. Mike's coming.
Hi. I was just wondering about Nanite tessellation. What are the main sort of performance concerns surrounding that? Because I know that it's more expensive than just a static, pre-tessellated mesh, but I was just wondering what the sort of concerns around that might be.
Yeah, so obviously your Nanite tessellation is not baked at import time, so it's not offline calculated. There are definitely some performance considerations to think about with it. Maybe Jack has probably a better answer to this than I would.
I haven't looked into it too much, I'm afraid.
No,
so yeah.
I've done a little bit around it. It's you still want to be careful with the type of asset you're doing it on, and potentially still the number of vertices and meshes that you're doing it on, but I haven't looked into it too deeply. It's been used a lot in landscape, which comes to it with some really cool results, but I don't know what the performance impact cost on that is yet. I'd say stay tuned. There'd be more coming on it. Yeah.
Thank you.
Do you have a question, Dorothy, on anyone?
Hello. So we hear a lot about how Nanite can help support other systems like Lumen and just the shadow virtual maps and etc. How does Nanite help in other case scenarios with like stylized games and low poly games to contribute with that, with those systems? Like, again, one year example with overdraw on low poly meshes would be a problem, and Nanite wouldn't know how to handle, but you still want to use Lumen, and Lumen would better work with Nanite. Is that like something that I would still want to look into?
Yeah, so there, so if I understand the question, it's sort of like, is Nanite still something I want if I'm using Lumen and other stuff? There is a slight more efficient rendering path and a slightly faster rendering path when using Nanite and Lumen together. Same with virtual shadow maps. It's just a slightly more efficient pipeline, I think, is my understanding of how that works. I've always gone with if you can nanite it. It's generally the way to go. It helps even with the small stuff, yeah. And I mean, there is something else I probably forgot to mention is, like if I spin around the camera and spin back, am I losing all that data? There is some cache invalidation where it will hold those, those clusters close to the GPU in case you do flick that, flick around a movement. So it's not like only for like static scenes or slow moving either. Any other questions? Thanks, Jack.
Thank you. How do you establish, not so much a Nanite question, but more general, I guess, performance optimization question. How do you establish early on what kind of budgets that you're going to need? It used to be triangle counts, obviously not so much with Nanite anymore, but perhaps like shader instruction counts. How would you early on establish those so that you don't end up with, artists putting all these big, complex scenes together, and then all of a sudden you're like, well, we're not even close to hitting performance.
That's a great question. I've heard budget talk about in terms of milliseconds, is how much milliseconds are we going to spend on Nanite, on target hardware. Jack and I were actually discussing this a little bit earlier, how we might automate performance profiling. How do we make that part of our sort of, our standard pipeline? I don't know if Jack wants to speak a little bit more to that, because I know you've been kind of investigating.
Yeah, I guess my thought on that is that Nanite isn't different. Like, I'd agree with what you're saying, set a budget and stick to it based on a technical vertical slice that you build of your scenario when you understand what features you want, and then you say, okay, that's what Nanite's costing us. Let's try to stick to that target, set up something like automated performance testing to let you know if you go over that budget and do something about it. This means that you're not I agree with you, don't optimize if you don't have to, but be aware when you do.
Yeah, there are there are cluster limits that you will get a warning as well in the editor if you start, if I go back to my tree demo, which is on 8, generally you'll see right at the top that I'm hitting really close towards the sort of the max cluster warning amount. There are techniques you can solve that in terms of at a certain distance disable Nanite entirely and switch back to a LOD chain. So you might just go back to a 2-card mesh of a tree. So some stuff there. So yeah, I guess just keeping an eye on the thing. Regular Unreal Insight runs. This also can be helpful.
So we built a system where it was we had, just for shader instruction complexity, we had a system where we could just dump materials. It was just a small system we built, and then we would run it on the platform and say there's a bunch of flat planes but at different tessellations, and we would see what the shader performed at per tessellation count. But
that's quite cool. I like that.
Yeah, it is cool, but we weren't sure in the end how well it translated into a real scene, because obviously a real scene is quite different. So we were never quite sure if that was a good translation in the end. But it was useful initially, I think.
It would be good extra data though, right? It's a little bit more data in the system, and when you're evaluating pixel programmable or in that GPU profile, I wonder if I've still got that up.
It's good for a comparative metric if you have multiple different shaders.
Yeah, and because it's listing all the shaders down here in our hardware and software rasterizer. Now, if you see one that you've got this one's got a high instruction count, and look here, it's got a few milliseconds, and I have 100 of those trees, then you can start using that information. I really like that tool. I think that's kind of interesting and worth exploring. Oh, geez, the rocket ship stopped. There's felt on here, and I'm not sure that the laptop's loving it. We've got 2 questions on the right-hand side. I'm glad people have questions. It's great.
In addition to, you said that Nanite doesn't like clustering over the edges, so it likes contiguous meshes.
Yep.
In addition to that and UV islands, is there any other major concerns for asset creation?
So is there any other tips and tricks around asset creation that you could do ahead of time?
Yeah, I've seen that it doesn't like to cluster over UV bounds either. It tends to create cluster edges along them.
Yeah, because it's looking at edges in some way, right? Whether it's the edge of the mesh or an edge of UV or something like that. I don't have a good answer to this, Jack. Just throw you under the bus here.
There's a few things that you need to look out for, I suppose. The PCG example, that's very built for that. We haven't seen tools like that, so I think it's so cool that you brought that up. The one quirk that, it's situational, right? So I'll give you, one example is that because Nanite is clustering, we have an option that you might have seen for foliage to try to preserve its volume. And so in this way, we can take traditional methods. But the point I'm trying to make is, it depends. I guess with that
the most
example.
senior
yeah.
programmer answer ever.
Yeah.
It depends.
But yeah, like I think thinking about PCG and expanding on that, watch that space, because that's such a good point and that's totally different. And how else can we approach that in different ways where we're preferring geometry over cards? Asking people to not use cards is scary because we don't have tools or pipelines that are good at that, really. So yeah, it's
The
interesting.
traditional way we've always made trees
Yeah.
is masked geometry, and it's not great with Nanite. It likes just full geometry for the whole leaf. Don't put any masking on there. This wouldn't be the be-all and end-all of making trees. It's an interesting approach, but I would say keep an eye on what's coming down for Nanite and foliage. There'll probably be more stuff hitting it soon. It's a changing landscape. There was another question a couple of rows back.
I think this might be the last.
Last question.
From the artist side of things, with Nanite, should artists be worrying about the poly counts of their assets, or can they just make, say, a rock with 1 million polys, chuck it in engine, let Nanite handle it?
It depends. Nanite likes large amounts of geometry. Its algorithm works best with it. Does that mean it's best for your game? Maybe. I still think the traditional sort of approach still applies here. Is like, how close to the camera is that rock getting? Do I need that detail? I don't think any of that really changes. And it depends on the style of your game as well, but I think, 1 million polygons on a rock is probably not the worst anymore as it used to be, but and if you stay far away from it, you're never going to hit that, that high LOD that you would normally see anyway. So it just depends. Yeah. Sorry.
Thanks very much.
Yeah. Cool. If you have any more questions, I'm hanging around. I'll be around and about. I don't think there's any other talk after this anyway. So if you want to chat, I'd love to talk about what you guys have done, what you guys have tried, so I can steal it. Cool. Thank you very much, everyone.